Yeah, I was mute. But this is just a review of your lecture 11, so don't worry. Just watch your lecture 10 when you're watching the recording, and you're good. Uh, so I'm just reviewing that. But if you haven't watched lecture 10, if you're watching the recording, just pause here, go back, watch that lecture, and then come back. I'm just giving the review for the class. All right, so let's continue. So the biggest problem with the superscalar is the dependency, the raw dependency that we had, the control dependency that we had. And that problem is kind of significantly worse because you cannot really like feed two instructions that are dependent to each other into the same pipeline state. In the past, I could do forwarding, for example, from here to here. But if I put two instructions that are all in the same cycle, then the forwarding doesn't mean anything. You cannot do the forwarding, okay? So the forwarding problem and the raw data hazard problem is even worse. And then the checking itself is also significantly more expensive because now I need to do many checks because there are two instructions at one cycle, there's two other instructions at another cycle, and I need to do all these checking all at the same time. So superscalar is kind of a good idea in terms of, possibilities, but by itself, using the kind of the ideas that we had before is not going to be enough. It's not going to give us the performance that we need. So how do we fix this? We go with what we call an out of order execution. Okay. So basically, the idea of the out of order execution is, can I basically run things out of order? There will be multiple problems that I'm going to go over in this lecture, but basically the idea is I'm going to still, fetch and decode in order. So this part will be in order, but I'm going to create a mechanism such that the instructions that are independent from each other can be easily found, and then I can feed these instructions into my pipeline independently from other instructions. In this way, if I have a superscalar processor, then I can, always fill the pipeline stages as much as I can. The difference between in order and out of order was in order processors was kind of limited in the sense that you can only go with the program order. So if, for example, you have like in sequence of instruction of I1, I2, I3, and so on, if I2 is not executed, you cannot execute any of these future instructions, or younger instructions. But out of order basically kind of relax this assumption and say that if there are instructions that are independent from this instruction, I can basically kind of let them to go inside my pipeline. The beauty of this and the advantage of this is then you don't have to need to be worried about all those raw data hazards and so on and so forth. So you can always kind of feed your pipeline, your very hungry pipeline that can run multiple instructions, like 4 instructions at the same time, with this idea. Okay. So now the big question is, how do we do this, right? So how do we get out of order execution? And there are 3 main problems that kind of coming out of this out of order execution that we're going to talk about one by one. In lecture 10, I kind of talk about this. I'm going to quickly review this, and then we're going to talk about these 2 others that are more important. You had a question?
Yeah, it's from the previous slide. There's 2 blocks. One is called complete and one is called retire.
Yeah. So the question is, what's the difference between complete and retire? That's the one that I'm going to talk about. That's actually what I discussed in the lecture 10, so I'm going to review it quickly. Any other questions? So in order to understand what sort of basic problems we're going to get from out of order execution, you have to think about a simple scenario like this that I'm showing you here. And that's like one of the very first problems that we're going to run into once we start doing out of order execution. So consider like a sequence of this that you have I1, I2, all over to I9. And then let's say you have like your pipeline and then your completed instruction. If you have an instruction like this, that let's say that this is a branch instruction, in the past, the way that this would have been worked is you kind of like go through the kind of the sequence of instruction. These 3 instructions would be completed, and this I4 instruction, for example, gets to the mem stage, At this point, you have already kind of fetch, decode, and execute 3 other instructions, the next few instructions. But at this point, for example, you kind of realize that your branch was taken. So you should kind of flush these instructions, right? We talked about this extensively, and hopefully you've done your quiz and then you know how this works. So far, so good. I've shown you how this can be done in a pipeline processor. So you flush this, and then you kind of go and fetch the right instruction. For example, let's say I8 is the right instruction. So you complete that. Nothing bad will happen. But now let's consider an out of order execution scenario for the same sequence. Now I'm kind of giving you kind of a special circumstance here. And let's say, again, you have the same sequence of instructions, but now let's execute these things out of order, okay? And now, since I'm doing this out of order, let's say, for example, my I7 managed to kind of, get ahead of the rest and managed to get executed faster than I4, okay? So looking at the same pipeline, now I will have something like I4, I3, I5, I6. I'm just showing you like just a basic example, just a random example. So things are out of order, as you can see. So I4 is before I3. But the important thing is that if this I7 managed to kind of get executed sooner than the others, there will be a possible scenario where I7 is already finished even before we start executing I4, okay? So what will happen if this I4 is still a branch instruction? Then if we want to flush things, we will, like, previously we would flush all of these things, right? So we can flush this, and that's not a big problem. The big problem, though, is this I7, because in the regular program order, these instructions should have all been flushed, right? And I should have, for example, continue from I8. But since this I7 is already completed, there's no way of kind of going back to the system and recover this, because this already left the pipeline. So there's nothing there to flush, okay? So if I kind of like, naively kind of out of order execution, like, reorder these instructions, if there are things like branch instruction that change the order of your pipeline, then you will run into very, very serious problems like this, that you have an instruction that is, executed out of order before the other instructions, and this should have happened, all right? So we should have prevented this if we had the in order, okay? So this is a big problem that we have in out of order execution, okay? So how do we fix this? We fix this by introducing this new kind of concept, this new stage in our pipeline called retire, okay? So the retire is separate from completion. In the past, we kind of like say, okay, the instruction they execute and then they complete, which means that they kind of write their data into some form of, memory or register file. But now we kind of separate these two from each other. That once the execution is done, we call it complete. But once the result is being written to the main memory or the register file, we call that retire, okay? So there is a separate kind of definition between these two, okay? So by the way, retire also called commit. So some people call it commit, some people call it retire. In this class, we mainly just use the word retire. But if you've seen commit, it's the same thing. So if you think about retire and what's the difference between completion and retire, you have to think about what does it mean for an instruction to finish, okay? And if you think about that, it's basically for an instruction to finish, one of these three or all of these three or some of these three will happen, okay? So you either like write the data back to the register file. This is kind of like a permanent thing that you do. Similarly, if this is, for example, a store instruction, you write it to your data memory. Or if this is some form of a control flow instruction, you kind of update your PC. So you basically, your instruction finishes by writing some, final data to some sort of storage, right? The storage could be your register file, it could be your data memory, or it could be your instruction memory, in other words, PC, okay? We call this writing to the architectural stage. So basically, once things become visible to the architectural stage, say that this instruction is finished. And the important thing about this is that once you write to these kind of permanent storage units, there is nothing to come back. There is nothing to recover. You cannot recover the older data that you have rewritten, right? You cannot figure out where you have written this, right? So that's why it's important that this stage should be only happen when we are absolutely certain that this instruction has to be executed. Okay, that's how we actually kind of like differentiate between the two. So retire only happens that when we made sure that this instruction has to be executed, versus complete is basically when we kind of wait, we are not sure whether this instruction has to be really retired or it should be flushed out. Okay, again, I kind of like give a little bit more explanation in lecture 10, so watch that to kind of review this. So this is where like the first thing in out of order execution come into the play, the difference between what we call a complete and what we call retire. So the biggest difference is that the complete happens out of order. So for example, I7 can complete before I2 or I3. So this can complete before this. But the biggest difference is that I7 cannot be retired before I2. So basically we retire in order, but we complete out of order, okay? And how do we kind of save that data, that kind of temporary data? We introduce this additional thing called reorder buffer, or ROB, which essentially this buffer, that things that are completed gonna write themselves into this ROB. And this ROB is basically this buffer that's kind of whenever we want to retire things, the data that we have written to the ROB now is going to be written to my register file, to my memory, to my PC, right? So basically the trick here is that instead of writing things directly to my register file and my memory and my PC, I'm going to write things to this ROB, which is this temporary data. And then when I'm absolutely certain that this thing needs to be written to this permanent storage units, then I'm going to write from ROB to those storage units, okay? So that's the difference between complete and retire. Complete is happening when you're writing to your ROB. Retire is happening when you're writing from your ROB back into your kind of a storage units, okay? And then essentially you always follow this very basic instruction that you only retire instructions if all the previous instructions in the ROB has been retired. So I7 can only be retired if I1 to I6, all of them have been retired. If they are all retired, then it's safe to retire I7, right? So you might ask, how does this work? Why this would work? Considering the same example that I had before, now let's actually add a retire as well. So this way now I'm basically completing instructions, but I'm not retiring instruction. So now if, so first of all, for example, I can retire these two because these are the first few instructions. So I can kind of get rid of these two. So I can put this I1 and I2 here. But I cannot put I7 as a retire. Why? Because I3, 4, 5, and 6 hasn't been retired yet. So I7 has basically needs to kind of stay in this complete stage until 3 to 6 are all retired. So the good thing about this is what? The good thing about this is when I4 is in the pipeline and when we decide that we need to flush things out, we're going to flush all of these things. And we're going to also go into our kind of ROB, this buffer, and we're going to flush everything that is in this buffer as well, okay? This way, it is guaranteed that nothing bad will happen because only I1 and I2 is retired, and they're supposed to be retired because I1 and I2 and I3 is actually before I4, so they are supposed to be retired, they are okay. But everything after is not retired. And then the nice thing about this is, again, if you look at this here, you will see that I7 is kind of there. And if your branch is actually, be not taken, then if you're supposed to continue, then you kind of save a lot of time by pre-computing and pre-executing I7. Because like at some point, I4 and I5 and I6 will reach to the complete. And then there you can actually, retire all of them at the same time. And then boom, you get the performance that you want. Okay, question.
You need to flush out the entire buffer, or could you just get away with like flushing everything after the
Yeah, the question is like, if I want to flush, should I flush everything or should I basically just check the only instructions after? Yeah, these are like minor optimizations that you can do. So for example, if in this complete stage, I had I3 and I7, and then I supposed to flush things of I4, then I can probably keep this and then just flush this. That you can do, yes. So the question is, so you ask me how long does it take for you to resolve?
No, for your.
So the question is like, why are not we predicting taking, right? Or yeah. So I mean, this is just a hypothetical example. So for example, you can predict taking and then you realize that you made a mistake. I mean, branch predictors are not 100% accurate, right? So you generally, this is the example of if you have a misprediction, either predicting taken and it happens to be not taken, or the other way around. Generally, if you need to flush, and then if you execute things out of order, there will be scenarios that will be correctness issues. Yeah.
So the retiring just means like you're using kind of right back?
Yes, retire is your old right back. But you only retire in order, which means that if I7 is completed, you don't write it back until you're sure that I6 and beyond are all retired.
You're still doing whatever operation required to say the very last stage.
Yeah. So for example, if you need to write it to register file, you write it to the register file. It needs to be written to the memory, you write it to the memory, and so on. So yeah. No, before behind it.
So if I force to like say I8,
Uh-huh.
then what I5
Uh-huh.
how would I take into retirement if I5?
So the question is, if we have a branch like this, and then I8 would be kind of like an instruction that eventually gonna get into the retire stage, wouldn't you kind of like, how do you know that this is not retired? So basically, we're gonna have what we call a head of ROB. So ROB doesn't really check the indexes; it checks the rows. So the rows is kind of like this, okay? And it's always just checks whether the previous row has been retired or not. That's all you need to check. So in this case, it will just check that if I4 has been retired. If I4 has been retired, then it will retire. It doesn't really check the index; it checks the previous instruction. Yeah.
Should you want to wait till I3 finishes or wait a minute?
Yes. So at some point, I3 will get into the pipeline. So I'm gonna actually so you're gonna fetch and decode in order. I'm gonna show you what we call a reservation station. So it's guaranteed that I3 is already in the pipeline when you reach to the I4. So that's not an issue. The question was, should I make sure that I3 finishes before even I run I4? That's a good question. I'm going to show you how we are guaranteed. Yeah.
When an instruction is retired, is it removed from the completed ROB table or just the head?
Yeah. So the question is, when the instruction is retired, what happens in the ROB? Yes, you kind of make it invalid. You remove it from the table. Yeah.
How do you determine the size if the ROB is circular?
Mm-hmm.
How do you determine the size of the ROB if there seems to be a lot of different?
The question is, how do you determine the size of the ROB? So it's a design decision. Typically, the size of ROB is somewhere between 64 to 128. There will be a scenario where your ROB might get full, okay? In that case, you have to stall the process, will wait for the instructions to kind of clear out of your ROB, and then you can continue.
Okay, so I guess the follow-up question, so if you get to a case where your ROB is usually filled, and let's say the last instruction you have to fire ROB is like a store order or something, like, and then the next instruction for the next like sort of chunk where you sort of is like a load word you start that have this tendency is you still have to stall the process, your bottleneck still then the ROB size.
Yes, the question is that in this case your ROB size becomes a bottleneck, and then yes, and then the answer to this is that usually your ROB is big enough that, so for example, you usually have like a 4-issue or 8-issue pipeline processor, and your ROB is significantly larger. So very, very rarely happens that your ROB gets full. So usually, you already have 4 instructions, and then after a few cycles, they will all pushed out. And then you can boom, you can flush out lots of them from the ROB. But yeah, it's possible that your ROB gets full and you have to stop.
in this case, we flush I3 before, even though it's before the branch instruction, so if we flush it, will it eventually go back into the pipeline? Like, how would that work?
The question is like, if, for example, I3 is already in the pipeline, how do we flush?
It is flushed already, so like, will it come back since it's before the branch, or would that still need to run?
Yeah, so there are various ways of like, if we flush it, how do we actually rerun it? Again, let me explain the reservation station later, and then you'll see how things will be scheduled. All right. So this is what we call an ROB, and then this is kind of like how it would look like. As I said, we still fetch and decode in order, and that's very important because of the questions that have been asked, like how do we make sure I3 is finished? It's because we are actually fetching things in order. I'm going to show you that how it works. But the execution and completion can happen completely out of order. So essentially anything can happen at any time. And then we're gonna put things in order batch. So we kind of like, shuffle things and then let them run. And then eventually I put them back into an in order buffer. So something like this. And then the way that we're gonna keep track of the instructions to kind of make sure which one is which is I'm gonna have a pointer. Think about it as something similar to the stack pointer that always shows you the latest instruction, which we call head of ROB. So in this case, for example, the head of ROB would be I1. If the instruction that was in the head of ROB reaches to the ROB, then that means that we can, successfully retire that instruction. So we retire this instruction, then we push down the head of the ROB one step down, and then we are waiting for this instruction. Since this instruction hasn't arrived, I cannot retire these instructions, although they are already finishes, right? So they already completed. I cannot retire them because I'm waiting for this instruction. And the nice thing about this is that, as I said, I cannot, retire this I3. The nice thing about this is once this I2 comes, then I can I can retire all these instructions at the same time. But of course, you cannot retire unlimited amount of instructions. Depending on your design, you can, retire multiple instructions. Usually, if your processor is an N issue processor, for example, a 2 issue or 4 issue or 8 issue, you can retire that many instructions. So it means that you can write simultaneously those many instructions. So a 2 issue processor, for example, you can retire 2 instructions per cycle. Even though you technically can, for example, retire 3 in this particular example, you don't have the capability of writing 3 things back to your register file. That's why you only can retire 2 instructions at the same time. If you had a 4 issue processor, then you can retire all these 3. Okay, this is just a design attribute of your system. Yeah.
And just a quick check, the amount of issues is how many, like, kind of multiples of each stage you have. Right?
Yeah, so the amount of issue is the multiples of that superscalar processor that you have. Like how many instructions you can read, how many instructions you can kind of like read from register files, etc. Okay. And then another, possibility is that if you have something like this, and then you realize that, oh, I2 should be a branch taken, then all you need to do is basically just remove these all future instructions from your ROB. So you basically flush all the future instructions from your ROB. Everything behind it was already kind of finishes, so you retire those. You only flush things, below that head of ROB. Okay. So what do we store in the ROB? I'm going to actually come back to this when I give you an example. There are basically many things that needs to be stored in the ROB, including like the values, the register names, store data, PC, etc., etc. I'll discuss this later when I'm actually talking about the actual implementation. So this would be kind of your updated data path. So basically what is changing now is that essentially your write back stage, which used to be like this, is now basically going up to this ROB, and this ROB is the one that's actually writing to your register file, with this blue signal is showing me here. And then all this instruction basically goes into the ROB. Whenever we are kind of fetching a new instruction, we create a new entry in our ROB. Yeah. Is the ROB managing the PC still? Good question. And yes, so essentially when you retire, remember when I said that when we retire is when we either write to the PC or to to the register file or to the memory. So when you're retiring, when we are leaving the ROB, then we are basically going to the piece.
Sorry, just a quick, so the ROB only retires everything once it's not when the ROB is full, it's when only like the end instruction and then everything that ROB is less.
Yeah. So for example, you will retire this instruction I1. The question was, when do we retire? So when this I1 is the head of the ROB, then you retire it. Okay. And then this is, again, just think about this as a particular register. It's a pointer. So everything that is there or below it, before it, will be retired. Yeah.
Sorry, quick question about the, I think you mentioned flushing on slide 33. For that one, is that, because you said everything before the current pointer gets removed, so this is.
Anything below, I didn't say before.
Oh,
Anything below, yeah.
Okay.
Because, for example, if your I2 is a branch instruction is taken, so all of these things that you fetch you shouldn't supposed to fetch them, so you have to get rid of them. And this was your data path before ROB, right? So this was what we had before, and this is what we have now, okay? So again, going back to this design here, there will be 3 issues that we're going to talk about. I already talked about this one, which is how do we do the recovery due to the speculation. So let's talk about the other 2. Oh, by the way, participation, USUR PBZ1. This is number 1. We also released the solution for quiz 1. Take a look at it. Let us know if you have questions. We're gonna also release the rubric for it. And you can take a look at the rubric. You're gonna have partial grading and so on and so forth. You will also have the opportunity to kind of do the regrade request once the grades are out. If there is, like, for example, you kind of didn't really follow the solution, but your solution might be correct. So don't worry if there's, like, slight differences between your solution and the homework, the quiz solution. Anybody else is still all done? Yeah. USURPBZ1. All right. Okay, so let's talk about the other 2. And let's talk about this one. So let's think about what will happen when we start doing things out of order. What will happen to our kind of raw data hazards? Is there going to be new hazards, and how do we fix them all together? Okay, so think about the old raw data hazard. So raw data hazard was the scenario that we read after write. So for example, we had add x2, x1, x3, and then 1 or 2 cycles after we have another instruction, which is sub, which is using that value. This was a problem that we had in our pipeline processors. It's a problem that we're going to have in any sort of pipeline processors. How did we fix this? We fixed this with forwarding, right? But now think about out of order execution, okay? So in out of order execution, there is a possibility that you run this instruction even before this instruction, okay? So if I run sub before this add, do you think forwarding would help? Anybody think that forwarding will help in this scenario as well? No one. Yeah, forwarding wouldn't help because you haven't even started, executing add, but you had sub already in your pipeline. So all those things that we said about forwarding won't be applied here because essentially forwarding only happens if you manage to run this before this, and then you can kind of like, forward the results back. So there's nothing to forward in an out of order execution, okay? And we call this a true dependence. And what this is say is that you cannot really execute things out of order when there is a true dependence. So when I'm writing and executing this, I cannot execute this before this, okay? I have to either stall the processor or find other instructions and then out of order. So scenario like this cannot happen in your out of order execution, okay? I'm gonna explain how do we schedule, but keep in mind that you never have a scenario like this that this would happen because this will lead to correctness issues. There's no solution for it. So this should never happen in out of order execution, okay? But so we call this a true dependence, and this is a true data hazard. But there's also the other three, if you remember, there was read after read and write after write and write after read. And we told you that those are not a problem in order. And we told you kind of they're going to be a problem in out of order. So here it is. So for example, consider a scenario like write after write hazard. So for example, we have an add instruction and sub instruction. Both of them has x2 as their RD. So both of them writes into x2. In order processor, this wasn't an issue because we always guarantee that this happens before this, right? In out of order, as I said, that since any kind of combination might be possible, there's a possibility that this thing happens before this. So I execute this first and I execute this next. So what would happen in this case? What will happen in this case is that the value that we're gonna get out of these two executions is going to be the value created by this instruction. Whereas in this case, the value that created by these two instructions would be the value that created by this sub. So essentially, the actual value that we are getting out of x2 is different depending on the ordering of the instructions, right? And which ordering is correct? The ordering that is correct is this ordering. It's the ordering that the programmer assumed that it was. So you should follow always the program order when you're deciding which value should be written. So a scenario like this also creates issues in out of order execution, okay? But there is a simple solution for this that we're going to talk about. That's why we call this an out of order dependence, and we call this a false dependence, okay, in some sense. Because there might be some solutions that could fix this. There is no solution for the raw, but there is a solution for this. I'm going to explain this in a moment. Questions, yeah.
So for this specific instructions, wouldn't it not matter like add or subtract which one like happens first, or is it because like we don't know what's happening to the RS1 and RS2?
So the question is that why does it matter that the ordering? Because, for example, consider x1 and x3 different numbers, right? So for example, if this one is 10 and this one is, I don't know, 5, and then maybe x4 is another number 15, then if I add them, it would be 15 is equal to x2, and then I will do 15 minus 10 minus, so at the end here this would be equal to -5, right? But here it would be equal to what? It would be equal to 15, right? Because x1 and x3 are 10 and 5. So if you actually look into the value of x2, in this case is -5, in this case is 15. So of course it matters that which one is x. Yeah.
This issue, are we like retiring in order? So we're like that not be an issue to do with?
The question is, aren't we retired in order? And wouldn't this be an issue? Yes, but think about all this instruction in between these two that will use the value of x2. How do you going to guarantee that they are not, So there are a whole bunch of things that happens in between. Since you're kind of executing out of order, then they're not correct. Yeah. It wouldn't be a data hazard, right? If I, for example, if I run this and then there is another instruction that use x2, and if I run this after this, then there won't be a data hazard, right? If x2 is already finishes, there won't be a data hazard. All right. There's also another one that is right after read. And then in this case, I have a read and I have a write. And we call this what we call an anti-dependence. And again, if I change the ordering of this to, then again, the value that I'm going to read in x2 will be a different value. It shouldn't supposed to be like that, but it is, right? So again, ordering here has a significant impact on what is the outcome of x2 and any other instruction that use x2, right? So how do we fix this? We call these two false dependencies. The reason that there are false dependencies is that there's a simple solution for them that can be fixed, versus this one is what we call a true dependency. The difference between those two is that assume that this very simple kind of fix to this problem. Consider that instead of using x2 and x2, for one of them I used x4 or x5, okay? Given that these two numbers are kind of independent from each other because you're kind of writing things to it and replacing that same number, I could have just used a different register and always use that different registers, okay? If these two happens to be mapped into two different registers, I never would have that issue because considering a scenario like this, it doesn't matter which one I execute first, right? Because this value is written to x5, this value is written to x5, this value is written to x2, okay? So the ordering is no longer important because these are two separate registers. Same story for right after read. If I use this as a separate register, if I use the destination register as a separate register, then it doesn't matter which one is executed first because the source is different than the register, the destination, and I'm good. The one that I cannot really do anything about them is that when there is the actual true dependence, when the value of this instruction is actually dependent on this instruction, okay? Consider that these two values are not dependent to each other because they're two separate, kind of data that's been written. But these two are really dependent to each other because the value of this directly impacts this, but the value of this does not impact this, right? So what is happening is that if I manage to find a way to kind of avoid this kind of duplicate our destination register kind of mapping, then I will be good to go with these two. So I don't have these two issues anymore. I'm kind of back into what I had in in-order processor, which was a true dependence, which was the raw data hazards. I need to fix that in some other ways that I'm going to describe. But this additional kind of fake dependencies or false dependencies can be fixed if I basically just use a more intelligent way of mapping destination registers separately, okay? So this is what we call renaming, okay? If we rename the destination registers correctly, then I won't have these false dependencies. Again, I'm going to still have the raw data hazard dependency, and I need to fix that using some other methods. But the false dependencies can be easily fixed using this renaming logic, okay? So what is renaming? So the renaming is based on this assumption that we have two separate set of registers, okay? There's a set of registers that we call architectural registers, and there is a set of registers that were physical registers. Back in the day when I was describing the data path, I told you that these are the same thing, that I said that essentially we implement a register file with exactly 32 registers, right? And we call them x0 to x31, right? In reality, though, your register file is actually much, much bigger than that 32 registers. You might have 128, 256, 512, so on and so forth. You might have many, many, many registers, okay? So what's the difference between these two? Those real registers, those that are actually implemented on the register file, we call them physical registers, okay? And this could be 128, 256, and so on and so forth. The registers that you use in your ISA, specifically for RISC-V, these are x0 to x31. these are what we call architectural registers, okay? And what we can do, the trick that we're going to use to kind of do this renaming logic is basically mapping one architectural register to multiple physical registers, okay? If I can do that, essentially what I can do is that if I scenario like this, that my architectural register, which is X2, there are multiple of these X2, X2s, what I can do is that I can map this into, let's say, P2, and this P means that this is a physical register. And then I can map this to another physical register, let's say P3 or P4 or whatever, okay? So I'm mapping the same architectural register to multiple physical registers. And these physical registers are those that are actually independent from each other. So I'm kind of eliminating this problem that I'm having here, okay? So let me give you more detail. So the reason that we have this architectural register, first of all, is because that my ISA only understands RS1, RS2, and RD. And those numbers, if you remember, was always 5 bits. Because I cannot have additional space in my machine code to add more registers. Because if I want to add more registers, I need more bits for my RS1, I need more bits for my RS2, and I don't have that space, okay? So that's why we always stick to some fixed number for my architectural register. And when I'm writing my assembly code, I'm always using those, okay? But when I'm actually running this in real hardware, all I need to do is that when I'm creating the machine code, I can just have, when I'm creating the machine code, I just basically use those architecture registers. But when I'm actually executing this code, I can have kind of a mapping stage just right before the decode stage that kind of map this architectural register into some real physical register. So this is basically how we do it. We're going to use this thing called register alias table or RAT, okay? Which basically what it does is this kind of table like this that has multiple rows and basically a 2-column multiple row table. The left side of this table is basically your architectural register. So this would be your X0, this would be your X1, this would be your X2, all the way to X32, X31. So you need to have 32 rows. And basically what you save in this kind of table is the mapping between your architectural registers and multiple of these physical registers, okay? I'm going to show you how, but basically I'm going to say that X1 is mapped to P1 and P2, and then X2 is mapped to this one and that one, and so on and so forth, okay? And this way, whenever I see X1, basically I just go to the table and know which physical register is mapped to this table. What's the aliasing between them, and then I can use that when I'm executing the system, okay? So let me give you one more example, a bit more detail to kind of get you how this would work, okay? So I'm going to have this RAT table, as I said. For now, let's like make things simple, and let's say we only have 5 architectural registers. Let's say we only have X1, X2, X3, and X4 and X5. Okay, just 5. Okay, but this could be 32. Doesn't matter. And then I'm going to have the physical mapping of this. And let's say we have 10 physical registers. Again, make things simple. So for every architectural register, the potentially 2. So I'm going to have this RAT table. As I said, the left column is basically my architecture register. The right column is the one that I'm going to kind of populate. And I want to also have this additional register table called free pool. And this free pool is basically showing the physical registers that are not assigning to anything, okay? These are physical registers that are free, that are available to be used by architectural registers, okay? So 5 architectural registers, 10 physical registers, 2 tables, 1 RAT and 1 free pool, all right? So let's see how this is being used. So imagine that, the initial mapping of this would be something like this. So essentially you start with some form of like initial mapping. So for example, say X1 is mapped to P1, X2 is mapped to P2, X3 is mapped to P3, X4, P4, X5, P5. And since I have 10 physical registers, I'm going to put the rest of these 5 into this free pool. So basically P6 to P10, they're not assigned to any of these architectural registers, okay? So let's continue. So now let's say I have this set of assembly instructions. I have OR x3, x2, x1, add x4, x3, x4, sub, and then add on. Okay, this is basically your, your old assembly code. Okay, and now what I want to do is that I want to see if I can avoid scenarios like this. That, for example, look at this scenario and this one, right? This is what we call the output dependence, right? So you use the same x3 in both scenarios, but in reality, x3 could have been, x1 or whatever, and then we were good to go, right? We also still have things like raw data hazard between these two, but that's a separate story. But we want to kind of avoid scenarios like this one and this one. So let's see how renaming generally works, and then how we can actually, by leveraging these tables in this table, how we can actually fix this, okay? So I'm going to explain an algorithm that's actually implemented in hardware, and the hardware going to basically do this step by step, same way that I'm going to explain it to you in the next few slides, okay? So we're going to start by one instruction at a time, okay? So first of all, we're going to rename this first instruction, okay? So the renaming algorithm works like this, that we first look into my, my source 1 and source 2, in this case, x1 and x2, okay? So I put the instruction stays the same. I want to find a mapping, so I want to replace x1, x2, and x3 to the physical registers, okay? The first thing I'm going to do is that for my source registers, I'm going to check this RAT table, and I'm going to use the register that is mapped currently. So basically, x1 is P1, and x2 is P2. So I'm going to put down P1 and P2 as my source registers, okay? So that's the first step I'm going to do. The second thing I'm going to do is now I need to see what should I do with the destination register. For destination register, that's when the actual renaming happens. That's when we create a new mapping between one of the free pool registers, one of the free pool physical registers, and map a new one to the destination register. So basically what I'm going to do is that I'm going to look at x3 and say, okay, this is a destination register. I'm going to go to my free pool, pick the first register that is free, in this case P6, and I'm going to use that as my destination register, okay? So what will happen is that this OR x3, x2, x1 now becomes OR P6, P2, P1. And since now I changed the mapping of this destination register, which used to be P3 and now is P6, I need to also update the mapping between these two. So I'm going to keep P3, and then I'm going to update it to P6. And another thing that happens is that P6 is no longer free. Okay, so P6 is removed from my free pool. The mapping between x3 and P3 is now changed to x3 to P6. And then I basically rename my logic like this. So one question that you might ask is that when should I put this P3 back into this free pool? And the answer to that is no. The reason for this is that we're going to retire things out of order, and then there's a problem that I'm going to explain later. But for now, always remember that you're going to keep the older mapping inside your RAT table, and I'm going to explain it later why this is the case, okay? So you don't put back P3 in your free table. You only put back P3 into the free table when this instruction is retired. And remember, renaming is happening during your decode state, so it's still a long way for the instruction to be retired, okay? So let's continue with the next instruction. So now this is kind of my updated table. Okay, as you can see, I have P6 here. I used to have P3 here. I'm not showing it. And then the free pool is kind of, P6 is no longer there. Okay, so now I'm looking at this new instruction. And again, the first step to do is putting the add instruction here, and checking my source 1 and source 2, checking the table, whatever dependency whatever mapping I see here, I just put it there. So x4 is P4, x3 is P6, okay? So this is the first thing I'm going to do. This is how the slides also show it to you. Then I'm going to check this destination register, and this is x4, and I told you destination register has to be renamed, which means that I need to go to my table, and I need to change this X4 to P4 mapping to a new mapping. I have to go to my free pool, pick the first one, and put it here, okay? So I have to put P7 here. So basically, this is how this would work. So P7 is removed from my free pool. The mapping is updated with P7, and we continue, okay? We go to the next instruction, and again, first thing we're gonna do is that we're gonna check these two. X2 is P2, X5 is P5. And now I need to map and rename this X3. So it used to be P6, now it's going to be P8. So I'm going to put P8 here, and I'm going to put sub here, okay? So what is happening now? So consider the scenario where we had this and this, okay? I'll answer the question. Consider this and see why renaming is now helping us. So as you can see, in the past, this X3 and this X3 was the same, and I told you this is what we call an output dependence. But now take a look at how the renaming help us to kind of remove that problem, because now OR is kind of using P6, and now sub is using P8, okay? Exactly what I wanted, right? And again, if you look at this example, you'll see that there is a raw data hazard between OR and add, because X3 is being used in the next instruction. As you can see, I'm maintaining that raw data hazard here as well. So again, I'm not creating any correctness issues. I'm still maintaining the raw data hazard because that's not something that I can fix with renaming. Excuse me. But what I do fix is this output dependence between these two, which no longer exists in my system. All right, let me finish it, and I'm gonna answer the questions. And the last thing I'm going to do is an add-I. In this particular case, I'm gonna again look into RS1 and RS2. This is an immediate, so immediate does not need renaming because this is just an immediate. So I'm gonna put 2 here. I'm gonna check X3 and put P8 here. And then I'm going to rename X1 with P9, okay? So I'm going to put P9 here and add-I, sorry, P9 here and add-I here, okay? So basically at the end, this would be how my new table would look like. I still haven't freed some of these registers. That's why my kind of free pool kind of shrinked. But there will be a point that I'm going to free those older registers. I'm going to describe that later. So let me answer some questions. Yeah.
We ever run out of register?
The question is, can we run out of the registers in the pool? No, because usually your physical register is significantly bigger than architecture. If you do, then again, it's another candidate for stalling the processor. Yeah.
I don't follow why you're replacing register like X4 where there isn't a hazard. For example, X4 replacing P7.
So why are we replacing P7 X4?
The destination register, yes, where there isn't a hazard.
So the question is, why are you changing this? And then what was the second part of the question? Hazard?
When there isn't a hazard. Same question.
Why it's not a hazard? So what is happening here is that if you look at the destination register, right? This destination register is a new value, right? It's not dependent to the previous value. So you can always create a new and use a new register to kind of write that data into that destination register, right? So essentially, I have all the picks in the world to use my destination register. It doesn't matter which destination register I'm using. The reason I'm kind of following this algorithm is to make sure that I'm always using a new destination register. As a result, I'm always removing the chance of anti-dependence and output dependence because I'm always using a separate register, okay? So I'm basically, if you look at the results, I'm using P7 here. And again, I'm writing the results of P6 and P4 and write it to the P7. And then P6 is actually is really X3, which was the previous. So I'm not removing raw data hazard here, but I'm removing the output dependency. Yeah.
Follow-up question. So the older register, the older physical register, do you save their associations as well?
Yeah, so the question is, what do you do with your older registers? You still put it in the racks, okay? Eventually you write it in your ROB, okay? So you kind of like, once I show you the full everything together, you will see that your older register is saved in your ROB. And that's why when you retire, you know that which is your older register and you let them to go. Yeah, there was another question there? Yeah. Yeah.
So, it's like, and then we replaced it with 7. But does P4 go back in the P4?
The question is, when I'm replacing this for example, looking in this table here, when I'm replacing this P4 with P7, what happens to P4? Does it go back to the free pool or not? And the answer to this is that no, we don't let it go until we retire the instruction. Okay, so I'm going to explain why this is the case, because if you want to recover, you need to recover the old register. That's why you don't let it go. But I'm going to explain a little bit later. Yeah.
Are more physical registers always better, or if we kind of found an amount that's good to say that?
What do you mean by better?
Like having more physical registers, will that lead to speed ups?
Yeah, so the question is that whether having more physical registers leads to speed up, of course, because now you can actually have more mapping. So you can have multiple mappings. Yeah. And then you always have many physical. The reason that you cannot really have the same thing, like you might ask, why don't we do X0 to X40, X63, and then kind of we don't need the renaming logic anyway. Because if you want to change the number of architecture register, you need to change your compiler, you need to change your machine code, you need to change everything. But changing the physical register doesn't matter, because all you need to change is your hardware, and that's very easy. Yeah.
In regards to the free pool, do we have a mechanism in place to know which register is tied to which instruction?
So the question is regarding the free pool, do we have a mechanism to kind of know which registers are tied to which instruction? So free pool is actually the list of registers that are not tied to anything. So at the beginning, for example, you have 5. At some point, I'm going to free some of these guys and put them back here. For example, at some point, I'm going to put P3 back here, which means that this is again a free candidate, and now you can, assign it to a new instruction.
But in deciding when to read it or when to put it back, how do we know that it's tied to the retirement?
Oh, so in order to know when we can free, we put the number into my ROB. I'm gonna explain that later. So you're gonna actually keep track of your older register in your ROB. I'm gonna show that to you later. Yeah.
Is this process of renaming done out of order or in order?
The good question. The question is, does renaming happen in order or out of order? Since I told you that it happens during decode, and we do fetch and decode in order, so everything happens in order. Actually, if this happens out of order, there will be a correct decision. More questions? Yeah.
Yeah, so, based on what I can see here, does that mean that, the original registers for the original physical registers, P1, P2, P3, 4, 5 will never be used, or did they originally start in the free pool?
They started in the free pool. So someone asked that it seems that you kind of always kind of like actually being used, right? So for example, it's being used here in P1. So, but I'm just showing you a snapshot. There is like instruction before this and instruction after this on this. Okay. So this is how your renaming works, okay? So of course there is a quick question of when you be free, and we essentially free when it's safe to let your old destination register to go, okay? And when do you do that? When your instruction is basically retired. So for example, if I have a scenario like this, that if I have this OR instruction, which X3, X2, X1, and this has been renamed to P1, P2, P6, and it used to be P3 here, and P6 is now the new one. When this instruction is retired, what we are going to free is P3, okay? So we're gonna free P3 because this is the old destination register. This is the instruction prior to the instruction that I want to retire, okay? I'm gonna give you an example. You're gonna see how this would be helpful. But essentially, you always free the older destination register, not the current destination register. Yeah.
The table need to store the current and the previous.
Yes. So again, the question is, when do you store this? You either can store it in RAD, but as I said, you usually store this in your ROB. Okay.
So when we read an old register, do we have to update the RAD?
When we are freeing an older register, what should we do? All you need to do is that you put this in this register in your free pool.
So after we go through a bunch of instructions, at some point we just flush the RAD.
No, you don't need to flush the route. Yeah. So essentially, this is always something like this, that there is an older and they're newer. Whenever you have a new one, you put this older here and then the newer here, and then you just keep continuing it. Is it possible to run out of physical register? It is, but very rarely happen. If it does, you stall the process. All right. So this is the updated table. Okay. So the renaming Markov architecture is basically sits right after your fetch, right before you're reading your register file. And then one thing you to notice is that I changed the name here from register file to physical register file. This is to just tell you that this is actually when we are accessing physical register file. And basically the RAT kind of sits here and then kind of doing this for you. RAT is all, of course, needs to be kind of added with the ROB. So this is the updated picture, which you have the ROB and you have the RAT. And as you can see, the RAT is also connected to ROB because it tells the ROB which one is the older register. The ROB also tells the RAT when to free and then when to update. And RAT is basically, it has the free pool inside this as well. So I'm not really showing the free pool, but the free pool is within this module. So it's a RAT and a free pool within this kind of box that I'm showing here. Okay? Any questions? Cool. All right, so I fixed this problem. I fixed this problem. Let's talk about this problem. And it's kind of like, this is going to help you to kind of like, you know, connect all of these things together. You will see how we actually running things. Let's have a quick break and come back in 5 minutes and then talk about this.
All right.
Okay, so let's see how we actually execute things. And as I said, this is actually going to connect all of these things that we learned together. And then I'm going to give you a big example of when we're having all of these things at the same time and how we actually execute the instruction. Okay. So recap, we had ROB and renaming logic. Let's see how we actually schedule. Okay. So in order to understand the schedule, let's look at this, for example, where we have add x3, x2, x1, x4, x2, x1, x6, x0, x3, add I, x7, x0, 10. Okay. As you can see, there is, for example, a data hazard, a raw data hazard between this one and this one, right? So obviously this one cannot go, this I3 cannot go before I1 because this is a raw data hazard. But what we can do is, for example, we can push I4 before I3, right? Because I4 is completely independent from I3. There is nothing prevents us to kind of run I4 before I3. Okay, so we kind of need to know a way, a mechanism to understand which instruction is ready, which instruction is not dependent to the previous instructions, and kind of push that into our execution stage, right? And also we need to kind of a mechanism to fix this forwarding or data hazard, right? Because once, for example, this instruction here is finished. Let me just close this one more time and open it. When we are actually having this kind of like this thing here, we need a mechanism to kind of forward this data to this data so that we can then continue, right? So these two problems is kind of a scheduling problem, right? Kind of keeping track of when things are ready and then how do we forward, okay? So how do we do that? We're gonna add this additional unit called reservation station or RS. And literally the name is it's a station. Think about it as a station. Then instructions basically are fetched and they go and park themselves in this reservation station. And then whenever they're ready, they're gonna be pushed into the execution. Okay. So think about this as kind of like a very large lane of like you kind of like fetch instructions and put them into this reservation station. And think about it as execution is this unit that goes through this reservation station from this other side and see who is ready and then kind of pick them up and then execute them. Okay. So we kind of like, put this kind of lane or a station or kind of a pipeline stage or any memory, something like that, if you want to call it, that kind of decouple the fetch execution from each other. So you fetch, you rename, and you put them into reservation station. The execution is basically using some mechanism I'm going to explain. You're going to go through this available options and then pick at least the 2 or 4 or how many that we can issue and then put them into the execution and then we continue. Okay. So this is kind of the trick that we're going to use in the reservation station. So for example, the execution stage sees that these 2 green ones are ready. Then we're going to execute them. So we're going to remove them from the reservation station and go back to the next one and next one. So now that we can do this, there's also another optimization that we make. And that's how we actually kind of like, make this execution state kind of decouple from what we had before. Okay. So we're going to introduce this kind of like weird name called functional unit or FUs. And these FUs are basically, think about it as kind of like parallel lanes that they're all separate ALUs. So think about it as like many, many different ALUs that you have, which basically can just kind of run these instructions independently from each other. So for example, like maybe one of them can do the sub, one of them can do the add, one of them can read the memory and so on and so forth. And another thing that I'm going to do is that I'm going to consider my memory as another FU, as another functional unit, okay? And the reason I'm kind of showing it in this way is that FUs might take multiple cycles, okay? For example, your memory might take like 10 cycles or might take 2 cycles. Your multiplication might take 3 cycles, where your addition might take 1 cycle. So basically, this is itself within the FUs is a pipeline. Each stage is just one pipeline of this, okay? So for example, this can finish in 1 cycle, regular thing that we had before, but your memory might take in multiple cycles. And what they do is that once they finish, they're going to update the ROB because this is when the instruction is complete, right? So basically, I'm going to fetch the code. I'm going to put it in the reservation station. From the reservation station, I have multiple lanes, let's say 2 lanes, 3 lanes, 4 lanes, how many lanes that I might have. And I'm going to pick them and then put them into this execution units. Execution unit is going to independently take care of this, whether it's a memory, whether it's an ALU, whether it's a branch, whatever it is. And then I'm going to update the corresponding line in my ROB. And that's how I'm going to actually complete this instruction. And then the rest is basically how we retire, which I'm already explained. Okay. And as I said, you might have multiple functional units. So for example, even if you might have a 2-issue processor, you might have 4 different functional units. Okay. For example, one of them could be an integer add, which takes only 1 cycle. One of them could be a multiply, which might take 4 cycles. One of them would be a floating point operation, which might take many, many cycles. And the other one might be just a memory, which might be, again, many, many more cycles and so on and so forth. Independent lanes. All right. And I'm just consolidating all in one structure that I call FUs. Anybody else have a question? Yeah.
Like the instruction to take multiple cycles in that stage, right? How does it like know that it's not done? How does it know that's not done? So like some other instruction can't take its place here.
So the question is, how do we know that it's not done? So first of all, each lane knows that whether the instruction is within it or not. So whenever it's finished, so for example, this one knows that any instruction that goes inside takes like 8 cycles. This one knows that everything goes 1 cycle, right? So each functional unit knows how long it takes for an instruction to finish.
So it's like fixed size per each.
Yeah, fixed size per each. Exactly. Any other questions? Okay. So with this FUs, I'm going to do this like this, okay? So for example, I have 4 available lanes. And then what I'm going to do is that I'm gonna, each lane independently goes through this reservation station, see what is available, take it and run it, okay? So basically just think about these 4 different workers that has lots of boxes here, and then each one goes and grab a box and execute that. When they're done, what they do is that they update the ROB, and ROB will tell the reservation station somehow that this has been updated, okay? So basically, think about functional units as just workers, basically, okay? So this is kind of like the updated version of what we have. We're gonna have fetch and decode and rename. Everything happens in order. And then we put things into my reservation stations. Then we're gonna execute things. And basically this happens by writing here, it's the complete stage. And then again, we're gonna retire things in order. So the complete stage completely happen out of order because each lane can pick something from this reservation station, not necessarily in the program order, but in any order that they want. And once they're finished, they put things back into the reorder buffer. Reorder buffer going to retire things back in order. So that's how we actually make sure that everything works nice and correct. Okay. So how does the reservation station look like? The reservation station looks like something like this. So basically you have many columns, and then each row is basically the number of available things that you can put. So for example, in this case, I'm showing a 4 entry reservation station, but you can have like 128. And of course, you might again ask, can the reservation station get filled as well? Yes, it can. If it does, you have to stall the processor, okay? So what do we have in the reservation station? The first one is what we call a use, which means that whether the reservation station is being used or not. So typically at the beginning, they are all zeros. When the instruction is issued, we also make this 1 back to 0. This up is the opcode, basically whether this is an add or subtract or multiply and so on and so forth. Then we have source register 1 and source register 2. These are literally the numbers. For example, whether this is P1 or P2. Here we are basically saving physical register numbers. We also do the same for destination register numbers. And then the important, very important thing is this too, whether source 1 or source 2 are ready. And basically this will tell you whether this instruction can be executed or not. So if I write 0 here, it means that this source register is not ready, which means that it's waiting for some previous instruction. There's some form of raw data hazard going on here that this source register is not ready. As a result, I cannot issue this instruction, okay? If both of them are 1, if both of these are 1, then it means that this instruction is ready to go, and boom, we're gonna execute that, okay? If the instruction has an immediate, we're gonna save the immediate here. This FU basically tells you which lane this is going to be occupying, and the ROB number is basically telling you which entry of ROB is corresponding to this reservation station. Because the moment you put something in the reservation station, you also save an entry in your ROB, okay? All right, so with all these, let me kind of recap how the out of order execution works. And then I'm going to give you a big example of all these things together. We're going to actually step through a program 1 step at a time. And I'm going to show you how your reservation station changes, how your ROB changes, how your FU changes, and so on and so forth. Okay, so to kind of like give you an idea, this is the naming method, convention that we are using. It's very similar to what we had with pipelining, slightly different names. So of course, everything starts with fetching, okay? But since this is a superscalar processor, you usually fetch multiple at the same time. So if I tell you this is a 2-issue processor, you fetch 2 instructions at the same time, okay? So the fetching is the same exact thing that we were doing before. Then instead of decoding, we call it dispatch, okay? So dispatch is this process of basically putting instruction into the reservation station, okay? Dispatch happens, during dispatch, a big thing that happens is the renaming, okay? So the first thing that you do is that you rename the instruction, and once you rename it, then you put it into the reservation station, okay? And important things that you do during this putting into the reservation station is that you also reserve an entry into your ROB, okay? And then, as I said, if either your RS or ROB is full, you stall the processor at that point, okay? Which means that you let the execution go, but you don't fetch any new instruction, okay? So this is what we call dispatch, which is a combination of renaming and putting instruction into the reservation station. Then we have what we call an issue, or some people call it fire, which means that we look into this reservation station and then put things into my execution or functional units, and then we're gonna release whatever we kind of put into the functional units. Then we no longer need to save them in the reservation station, so we get rid of them in the reservation station. And then the reason that we are actually executing something is that all the sources should be ready, and there should be an available FU. So if there is an FU and all the sources are ready, then we're gonna execute this instruction. We're gonna what we call issue or fire this instruction. Okay. Then of course, when it goes into the FU, at some point you will be completed. We call this complete. Complete is basically means that we update our ROB with this data. And important thing that happens during the complete is that basically this is when kind of forwarding happens. We update the ROB, and the ROB let know RS reservation stations that the data has been updated. So if the source register is kind of dependent on that RD, now the source register is now ready. So basically we're going to go back to the reservation station and update the existing instructions, okay? So this is basically equivalent to what we had for forwarding, okay? And we, of course, we need to release the FUs. And the last thing that we do is the commit or retire, which means that we basically, at the point that this instruction is free to go, so we're going to write back the data to the PC, to the register file, to the memory. We're going to let the old register to go. So basically, we are releasing the register back to the free pool, and basically that's it. That's it with that by that particular instruction. And then we're going to continue this for every single instruction. Okay. So let me give you an example with all these tables together. So we're going to go through this one by one. Hopefully, after this, you will understand how this would work. You're going to repeat this for your homework and probably for your quiz as well. So you will get kind of like the whole idea. So what I'm showing you here is that I'm showing a sequence of 4 instructions, just 4 example instructions. And the things that I'm showing here, this is basically your ROB. As you can see in my ROB, I basically have 5 different columns. First column is the valid column, which is basically saying that whether this lane in ROB is open or not. Then I save 2 things. I save the destination register and old destination register here. These are the 2 things that I use in my RAT. I'm gonna save the PC, and I have this kind of flag that says whether it's complete or not. If it's 0, it means that it hasn't been completed. If it's 1, it means that it's completed. Another important thing that I have in my ROB is my head of ROB, which is basically here. This is kind of pointing at the beginning to the top of my ROB, okay? So at this point means that whenever this instruction is completed, I'm free to retire it. But if this instruction, and any of these instructions are completed, I cannot retire them until I retire this instruction, okay? So this is the story with my ROB, all right? So another thing that I have, and you have seen before, is my RAT table and my free pool. So again, consider the same 5 architectural register, 10 physical registers. At the beginning, I have this kind of initial mapping between them, okay? Then I have kind of 2 other things here. This is for functional units. So this is the ready. So this one is basically showing that whether your functional units are ready or not. In this particular example, I have 3 functional units. One is ALU1, the other one is ALU2, and the third one is memory. The difference between them is that ALU1 and ALU2 basically can do ALU operations. The third one can only do memory operations, which means that it can do a store and load, okay? And then this column here is basically telling you whether they are free or not, whether I can execute something or not. So if I execute something, they become not ready, become no, okay? And then similarly for my registers, to kind of keep track of who is ready and who is not ready, I have all of my physical registers. These are all my physical registers, P0 to P10. Sorry, P1 to P10. And at the beginning, all of them are ready. Whenever I have some dependency, I make them not ready. Okay. And then finally, I have my reservation station. And again, as you can see, reservation station is the same thing that I showed you before. Okay. So with this kind of initial setup, let's actually go and run these 4 instructions one at a time. Okay. So what is happening? So starting from here, I'm kind of showing you with this format that this is the clock cycle. This is clock cycle 0, the first clock cycle. And during that clock cycle, multiple things happens. You fetch and you decode, dispatch, issue, etc., etc. So I'm kind of showing you in separate slides. So let's say what would happen first? You first fetch 2 instructions, okay? So I'm going to fetch these and this. And as I said, this is a 2-issue processor. That's why I'm fetching 2 instructions at the same time. So first thing, I use my PC. PC at this point is equal to 100. I use 100. I go to the instruction memory. I bring 2 instructions. I bring 100 to 104, which is this load instruction. I also bring 105 to 108, which is the second instruction, which is add. Okay, so I bring in 2 things at the same time, and I fetch 2 instructions. Okay. Then what happens? Then I need to what we call a decode or dispatch, right? So I decode this, and basically the decode part is the same thing that we were doing before. I put the opcode to my controller signal, the controller issue control signals, and all those things. Again, nothing happens in terms of like out of order. It's the same old story that we discussed in the pipeline stage. And then, so this is basically, this was, cycle 1. I just fetched 2 instructions. There's nothing else I can do in cycle 0. So now I go to cycle 1. So I need to decode those 2 instructions that I fetched. I also need to fetch 2 new instructions, right? So I decode these 2. I also fetch these 2 new ones, okay? Again, same story. Still nothing new in terms of out of order execution. Then we go to this 3rd cycle. So I fetch and decode in cycle 0, cycle 1. Now I go to cycle 2. In cycle 2, that's when things start getting out of order. Execution gets relevant here. So I need to rename the decoded instruction that I decoded in the previous cycle. So these 2 instructions that I decoded in the previous cycle, now I need to rename them. Okay. So how does the renaming work? If you remember, I told you that basically I need to go over the source registers first. So in this case, X1 and 0 are my source registers. For immediate, I don't need to do the renaming. For X1, I need to go to the table. I see that basically my previous mapping between X1 was P1. So I have to put P1 here. So I put 0 P1 here. I need to change this X2 to a new register. So basically what I need to do is that I need to change this to P6, okay? So what I will do is that I put P6 here, and I remove this P6 from the free pool, right? And that's it. And I'm also gonna remember the older register number 2 in this rat table as well. So 6 and 2. And then since this is a 2 issue, I'm going to do 2 things at the same time. So I'm going to also rename the second instruction here. And again, the second instruction happens before this first instruction. As a result, this should happen after this. So now I'm looking at the new kind of mapping and see that X2 is now mapped to P6. That's why I put P6 here. I look at the X3 and I see the mapping says that it should be P3. So I put P3 here. And for X4, I need a new mapping. So I change the old mapping, which used to be P4 to P7. I remove P7 from my free pool. I put P7 here, and that's it. I'm going to put P7 here. Okay. So this is going to be how my renaming logic would work. I'm going to give you a moment to look at this and let me know if you have questions so far. Any questions so far? Yeah.
Renaming, like, that occur in the same cycle as the decode? I think there's a decode.
No, it happens in cycle after. Yeah, that's why we are at C2 right now. Any other questions? Yeah.
Kind of old question, but the use column of the,
Reservation station.
yeah,
It's just to telling you whether this row is being used or not. For now, none of the reservation stations are being used, so all of them are zero. Okay? So the renaming is done. Another thing that I need to do at cycle 2 is I need to decode these two instructions. Again, nothing new, so nothing to show in this table. Then I go to the third cycle or fourth cycle if you use this naming convention I'm using. So C3. So I do the renaming. Now I need to do what we call dispatching. And if you remember, dispatching was this process of putting things into my reservation station. Okay. So how do I put things in the reservation station? And the moment I put things in the reservation station, I also kind of put things in my ROB. Okay. So what do I do? So I look at the first instruction. Okay. I look at this instruction here. Let me use a black color. And I need to kind of populate that into my reservation station. So what I do. So looking at this, I'm going to make this use now equal to 1 because now I'm occupying that lane in the reservation station. I'm going to use load word as my opcode. I'm going to use P6 as my destination register. I'm going to use P1 as my source register. And then whether or not P1 is ready or not, depending on this table here. So I see that P1 is actually ready. So I put yes here. The second destination source register is an immediate. So in that case, I just put 0 as the source register because it's X0 and immediate doesn't matter. I also put yes here and put the immediate also here. Okay, so it's my actual immediate value. And then since this is a load word instruction, I need to use the second FU, right? So I put 2 here because remember that my FUs are, the first 2 are ALUs and the third one is the MEM. So I need to only use the third one, okay? And as I said, the moment that I put these things in my reservation station, I also reserve a spot in my ROB, okay? So what I'm going to do in my ROB is that I'm going to say that this lane is connected to the first lane in my ROB. So I'm going to save 0 here. All right. So this is it with my with my reservation station. Okay. An important thing that happening here is that the moment that I put destination register equal to P6 here, I'm going to update my ready table for 6 and I'm going to put no there. Why? Because this is a destination register. This load instruction needs to be completed such that this register becomes ready again. So the moment I see a destination register, which in this case is P6, I need to update this table and put no next to destination register, next to P6. Okay, so that's what I do while I populate this this reservation station. Okay. So that's it with the reservation station. So let's see what happens with my ROB. So in my ROB, I'm going to change this value to 1 because now I'm occupying this lane. I'm going to put the destination register here. I'm going to put the old destination register here as well. How do I get that number? It's this number here. So I'm going to put P2 here. I'm going to save the PC here. And then the complete is basically is equal to 0, right? So that's what I'm going to do. So let's repeat this for the second instruction. The second instruction is add P7, P3, P6. So I'm going to put it here, 1 add P7. The moment I put P7, I'm going to go and put a no here. Then I have P3. I'm going to check whether P3 is ready or not. Yes. Then I'm going to check P6. I'm going to put P6, and then that's where the important thing is happening, is that P6 is not ready, so I put no here, okay? Because before that, P6 becomes unready, not ready. So I put 0 here. There is no immediate for this instruction. I don't put anything here. And since this is an ALU instruction, I can either use FU0 or FU1. I just go round robin and start doing this. So I put 0 here, And then since this is connected to this first row number 1 in ROB, I'm going to put 1 here. Okay. What do I do with my ROB? I'm going to do 1 here, P7 here, P4 here, and 104 as my PC. And then, of course, my complete would be equal to 0. Any questions so far? Yeah. It's not redundant because when you're, so the question is that immediate column redundant or not? It's not redundant because when you put this into FU, you basically read the RS1 and immediate. So you need that value. So you need to store that value somewhere so that you can then push it into the FU. For example, if you add I, for example, you need to add RS1 plus the immediate. So you need that immediate into your FU unit. So basically, the way that FU works is that if it sees that it's actually there is a valid number here, it's going to use that instead of source register 2. Yeah. Question.
Is configuration for the FU fixed or like does it vary based on like the 2 issue or 2?
Yeah, so if the question is how does the configuration of FU changes? So this is something that you put in the hardware at the beginning. So for example, if you have a 4 issue, you probably have somewhere between 4 to 8 different functional units. But it's hard coded inside your design, so it's not going to change. But for a different design, you can have multiple FUs.
Okay.
Yeah.
This is an MUL stand for no.
Oh, this is the multiply. So for example, this one is also capable of doing the multiplication, but we are not using multiplication in this course. But it's just I'm just trying to show you that there might be small differences between ALU units as well. Yeah.
Question. So just a small thing, the immediate is the actual number that we're grabbing from the instruction.
Yes.
And then the second thing is the memory for the functional unit that also includes like the ALU for like the adding the immediate to it, right?
Yeah. Yes, that's all. Yeah.
What do you call the execution stage? Yeah. Booster every entry in the R.
When you want to select? Yes, you technically, so the question is, how do you select? You basically start from the top and then see who is ready and then you put it down. I don't really explain how the hardware works, but there's like, tiny bit of, checking that's happening and whoever is ready going to go. But yeah, in terms of implementation, is really, you just look through the entire table and see whoever is ready, you just put it down. Yeah.
For that view column, is that just the index of the
Yes. Yeah. So the question is that FU column is basically the index of that table. Yes. Yeah. How do we know? Say it again.
Like source 2 is not like everything's.
Yeah. So question is about how did we put no here? So if you look into the first instruction, you see that the first instruction is using P6 as destination. Okay. Since this is using P6 as a destination, I'm going to go inside this ready table, which is showing the readiness of my physical registers. And I'm going to put no here, okay, for the first instruction. In the second instruction, I'm going to use P6 as my source. And I'm going to go back and check this and see that, oh, there is a no there. So I'm going to put a no here. This is exactly the same raw data hazard that we have before, right? Yeah. P2 and P4? Why P2 and P4 are destination? No, these are all destination registers, so they're not ready. Yeah.
Oh, they're all.
No, so these are just the initial mapping. So let's say you start from here. Okay. So this is the very first instruction that you're gonna execute. Yes, in the past, this would have been no, because they were all destination registers. Yeah. The question is, what's the difference between ALU1 and ALU2? There is no difference. They're just two parallel ones. They're tiny different in this, my particular example. The difference is that this one is also capable of doing multiplication. The other one is not. But in regular cases, there's no difference. So, and then how do you decide? You usually go round robin. So you first do first one, then second one, first one, second one, second. Yeah.
saying which register is like available to have things stored in it?
Yes.
or-
Yes, so the difference between these two tables is that this one just says that what are the registers that haven't been mapped to anything. This one basically says whether there's an available data that we can use. Yeah, one last question.
For P6, right now, the source two is no.
Yeah.
After execution, after the first instruction is declared, do we go back and run it as a test?
Yeah, so basically what happens is that I don't have to go through the execution. That's one thing that I'm going to do next time. But basically when we want to execute, we're going to go and check whether both of the source registers are ready. If they are both ready, then we're going to remove this from the table and put it in the execution. Then we go, for example, to this one and see that this one is not ready. So this one stays in the reservation station until at some point becomes ready, and then we're going to push it back. So it stays until it becomes ready. All right, so I'm gonna pause here. I'm gonna come back to this example next time, and we're gonna finish it. All right.